Hello, and welcome to this session of ACS Science Talks, a virtual lecture series, scientific talks by specialists on specialized topics for a specialized audience. I'm Kunal Gupta, and I'm pleased to be your host for today's broadcast of ACS Science Talks. Our speaker for today is Professor Elena Galoppini. Professor Galoppini graduated with a MS in chemistry from the University of Pisa in Italy and earned her PhD degree from the University of Chicago in 1994, followed by a postdoctoral appointment at the University of Texas, Austin. She joined the faculty at Rutgers University-Newark in 1996, where she is now a distinguished professor. Professor Galoppini is an organic chemist, and her research focuses on the controlled functionalization of nanostructured semiconductor surfaces with chromophores and redox active molecules. Her group develops the synthetic designs of organic linkers as well as interfacial host-guest chemistry to control photo-induced heterogeneous charge transfer processes. These processes are of fundamental interest and also address important technological challenges in application fields ranging from solar energy conversion to electrochromic materials and nanosensors. Professor Galoppini has received several awards, some of which include the Rutgers Board of Trustees Award for Excellence in Research, Distinguished Service Award by New York Italian Consulate, and the Alan Berman Research Publications Award by Naval Research Laboratory. Professor Galoppini is also a Kavli Frontiers of Science alumni and is the founding deputy editor of ACS Applied Optical Materials. Thank you, Professor Galoppini, for joining us. The stage is yours.
Thank you very much for the very nice introduction and especially for this great opportunity. So I will just start by introducing the new journal. So as mentioned, I'm the founding deputy editor of a new journal of the American Chemical Society. It's ACS Applied Optical Material. The journal was launched in June of 2022, so it's very young, it's not yet 1 year old, and appeals not only to chemists, but also material scientists and physicists, engineers that work in optical and photonic materials. And you can follow us on e-alerts, sign up for e-alerts, and read the journal. We have already 2 issues, about 100 papers, including the ASAP. And so you can learn more about the content and scope of the journal. The journal, the editor-in-chief of the entire AMI family, it's part of a broader portfolio, is Professor Shantz, and in particular the deputy editor of this particular publication, the new journal. I'm very excited to have a great editorial team. There are 4 associate editors, and they are covering the area of interest to the journal, from photonic and plasmonics, that's Professor O'Carroll, phosphor and inorganic emissive materials, Professor Liu. Professor Song is an expert in display material and devices, and Professor Garcia is a physicist with experience in laser, nonlinear optics, and photonic crystals. And I want to point out that this team is, as you see, geographically very diverse. It's coming from not only from the US, but Taiwan, Korea, and Europe. I'm excited also to work with a very diverse geographically team of associate editors, editorial advisory board member. The scope of the journal is the best thing to understand the scope of the journal is actually start reading the issues, looking at the content. But as you see, it's fairly broad. And effectively, there are 3 elements to keep in mind if you are interested in submitting your work to this journal. It has to involve, obviously, optical materials, and application has to be applied chemistry. That doesn't mean that you have to demonstrate a functioning device, but when you write your manuscript, make a good connection to relevant technological applications like the ones shown here. So you can ask me later at the end more about the journal. I would like to just show the very first cover and mention that is part of a larger applied material interfaces portfolio. We are the younger member of this family, and that has been very successful, each of these journals, and we hope to grow as and be as successful as the others. So now I would like to start the topic of today's presentation. As I mentioned in the introduction, I'm a synthetic organic chemist, but for many years I've really worked with the inorganic semiconductor, and my group has been interested in developing and engineering. It's a bit a strong word, but really functionalizing these interfaces between chromophore or redox active material and metal oxide semiconductor. These are important interfaces. I will explain why. And today, after I do that, I will focus on the role of molecular design, what a synthetic chemist, how a synthetic chemist can contribute to this field. I will bring one example of research in this field from my group. It's not a very new, but I think it's a nice story that it's finished. So it's maybe good to present in this context. And then a little bit conclusion and outlooks. And I hope that I can discuss this further with you. So electron transfer at interfaces, organic, inorganic interfaces, is very important in a variety of fields. One of these is solar energy conversion, and for renewable energy. So it's a very important topic. And this involves a number of interfaces, charge transfer, number of interfaces, as you see here in this cartoon, and a number of scales. What I will be discussing today is one particular interface. We have been interested for a number of years, for many years actually, between a molecule, typically organic molecules, and metal oxide one-gap semiconductor. So these are have been found and still find application in a number of fields. Sensitized solar cells that convert sunlight into electricity, dye-sensitized photocatalysts, but also artificial photosynthesis systems where one can mimic or replicate what nature does in real photosynthetic biological systems. The semiconductor function is that of an electron acceptor. Following photoexcitation, the dye injects an electron in the semiconductor, but also can be interfaced with an electrode. And therefore, this can be exploited to generate energy or chemical solar fuels if you have a photocatalyst. The chromophore is the electron donor and the light harvester. And shown here are some recent, more or less recent or relevant reviews for this field, and the pictures were taken from some of these references. I wanted to mention a little bit more about the development of this interface. So dye-sensitized solar sensitization was known for many years. So since the 70s, the process of these interfaces have been studied. But in 91 was developed the very first dye-sensitized solar cell that really spurred great interest in this area. Now, with the discovery of the perovskites, there is dye-sensitized solar cells are limited to niche application. Perovskites are much more efficient, But I want to emphasize, the reason I'm showing this very nice slide for this publication is that from the beginning to the end, so over all these decades, the interface that is of interest between a semiconductor and a chromophore is still at the center. They're still relevant, is still interesting. So organic synthesis in the development of these very important junctions is still relevant and interesting over all these years, not only from the practical and applicative point of view, but also fundamental, because obviously fundamental chemistry is coming along with the application. So we'll focus on the molecular design, how it has evolved and why it's so important. So at the very beginning, when I shown the slide earlier, the chromophore or dye was bound covalently to the surface of the semiconductor to make a strong bond and also a strong electronic coupling with the semiconductor. And this was a simple attachment, so it's directly attached to the surface. This is the early work. Very soon, chemists realized that actually these attachment could be further developed in a more sophisticated way to understand not only for the device application, but also to understand the charge transfer, the electron transfer, these complex interfaces. And this is very early work that by groups that have contributed with seminal work in this area. And as you see, the attachment is a simple tether. Over the years, the organic chemists have greatly contributed to this area by creating a modular design. So rather than having the chromophore directly attached to a simple tether, one can really creatively design each of these components and finely tune every aspect of this interface. So you can change the anchor, the bridging unit, and the chromophore independently, almost in a modular design. And this is not just to achieve a better efficiency of devices of the photocatalysts, but also, for instance, to control the positioning of these active unit on the surface, to control injection versus recombination, to tune all these fundamental and technologically relevant aspects of this interface. An example is shown here, for instance, in this molecule. This is a classic push-pull dye with the chromophoric or the donor unit, and this is the anchor group. But you can switch around and put the anchor group on this side and put the molecule, let's say, upside down, head down on the surface. And these would be used in an N-type solar cell, and this could be used instead in a P-type solar cell. So molecular design can actually tune aspects like this. This slide shows also that the importance of each component, for instance, the anchor group. So the anchor group, you can have a huge variety of groups, functional groups that form a covalent bond, as not just for the attachment, but to obtain an electronic communication with the surface. And these are groups that have been studied over the years. And as you see, there is a high level of complexity. So for instance, even just a simple carboxylic acid can have different type of binding modes on the surface. And this adds significant complexity to the interpretation of data, for instance. My group has studied, for instance, tripod-shaped compounds. These can be used, the anchor group in this case can be used to attach the chromophore perpendicular to the surface, but also to space the chromophore from one another. And also there are click approaches that are interesting to create attach the anchor unit to the chromophoric unit. So this is just points to a simple aspect, a simple component like the attachment, the physical attachment to the surface. There is a lot of possibilities in terms of designs and also important effects on every aspect of this resulting device and properties. I spent a lot of time trying to make this slide because actually it was very difficult to put together something that could represent the diversity of the molecular design over the past 20, 25 years in this field. So I just want to bring a few examples, and I've been here a bit presented some work from my group mostly, but I wanted to point out a few examples. So for instance, this is a very interesting aspect of molecular design. It's a push-pull dice with a donor and an acceptor, and they can actually tune the homolumo so that these becomes light harvesters up to almost to the IR. Chromophores can also be designed to bind either planar or perpendicular to the surface, and that has important consequences for efficiency of a device. Distance effects can be observed by tuning the length of a linker. And this is not just to study injection and recombination, but as probes of the environment that the chromophore or redox unit is feeling at these interfaces. Photo switching effect, conformational effect, and also more complex design aimed at controlling and probing multi-step charge separation, both in dye-sensitized solar cells, for instance, but also in photocatalytic system. So these are, it's a bit of a messy slide, but give an idea possibly of the variety of possibilities that can be achieved from with this modular design of chromophore linker and anchor. And this is a nice perspective by Meyer in this field. I wanted to mention another different approach to make this host gas, this interface, and that is a supramolecular approach. One of the supramolecular approach can be rather than directly attaching the chromophore to a linker and anchor unit, one can encapsulate the molecule of interest in a host, and then the host is bound to the surface. So this is a field that likes to explore because synthetically and for other aspects much more challenging, but it has some interesting opportunities. For instance, organic dye tends to degrade and to aggregate on the surface of the semiconductor. In this case, the host molecule can act as a shield and prevent some unwanted processes. In other cases, the host has been used to encapsulate a redox unit, so a photocatalytic unit. So this is another approach to engineering these interfaces that involves significant synthetic design. Another supramolecular approach is the use of a layer by layer. This is a very clever approach in which one can have a multi-layer on this interface of different type of chromophore or redox unit just by dipping in solutions and forming salt bridges of different type of molecules. So this is again a supramolecular approach with a significant input from molecular design. Some of the in this area, another supramolecular approach that I find it's extremely clever are approaches in which the chromophore bridges two different kinds of materials, two different kinds of nanomaterials. So for instance, in this case, a quantum dot, or in this other case, a catalyst. So these are basically other ways to create a complex interface with significant effort, significant from the molecular design point of view. So I wanted at this point to switch from after the introduction to show one example of work done in my group that illustrates the relevance of molecular design of this linker anchor unit, what one can do. In the past few years, we have been interested in developing linker anchor units that contain a function, like a little machine shown here. So the linker in this case, it's not just a tether, an attachment point, but has intrinsic properties that can influence interfacial properties, for instance, photochemical reaction pathways or energy level alignment. And obviously, there is because of the time limit, I'm showing only one example. It's older work, I want to admit that, but the reason I'm showing this is because it's a bit of a complete story, and that is nice to tell. So I will discuss a little work done in the area where we have introduced dipole moments in a linker unit, and to tailor the energy level of the chromophore with respect to the conduction band on a semiconductor. So the dipole effects of these interfaces are extremely important. They have shown to shift the photocurrent onset potential, reducing the energy, for instance, for water splitting dipole layer. So you can really tune this energy level. Lower the open circuit voltage of solar cells, and shift work functions on metal, nanostructure metal. So there is the dipole has important dipole layers. These interfaces have important effects. So to test this effect, we designed molecules, a set of porphyrins many years ago, where we had a chromophoric unit, a linker, and an anchor. And the linker unit contained a dipole, permanent dipole, up, down, with respect to the surface to which are attached, or no dipole at all. And the expectation is that the presence of the dipole, depending on the direction, would shift the HOMO and the LUMO up or down with respect to the conduction band of the semiconductor. This is important because obviously the injection processes and device properties heavily depend on this energy alignment between the semiconductor and the chromophore. And this could be a way to tune it just by using an dipole layer between at this interface. So these compounds require quite, they were synthesized. I have to show a synthesis slide, obviously. And I just wanted to mention that these, so the linkers were synthesized with the dipole pointing up or pointing down, and then the chromophore was attached to them. And the design was carefully done because we wanted to avoid that shifting the HOMO-LUMO gap. These porphyrin units are almost perpendicular to the linker unit. And therefore, as you can tell from the absorption and emission spectra, in these three compounds with dipole up, down, and no dipole, there is basically no change in the HOMO-LUMO gap, and therefore we could run this test how the energy level was shifting without changing the chromophore too much. So the work was done. This work was not done in my group. The measurements were run in the Bartinsky group and the physics department in New Brunswick, and they prepare monolayer of each of these compounds on a single crystal zinc oxide, and measure the UPS of the monolayers, and determine the position of the HOMO. And what was found is that actually these dipole layer influenced the energy of the HOMO as expected in the direction that was anticipated, and more or less in the magnitude that was calculated based on the dipole moment, which was only, I think, about 8 dBs, and was not aligned along the axis of the molecule. So this proof of concept experiment demonstrated that the dipole linkers could be used to shift the energy level of a chromophore onto a semiconductor, but we wanted to have stronger directional dipoles and also simpler approach if possible. So we moved this to linkers that are made of peptides. Oligopeptides have a strong molecular dipole that goes from the N end to the carboxy end. And when you have 18 units in this particular peptide, 6 units, you have about an 18 dBi macrodipole, which would generate a shift of 0.6 electron volts. So it's a big energy shift that we would expect in this case. The use of a peptide looks a bit strange, but actually it's not. The peptides are used to generate large dipole moments at metal interfaces. Here are some examples of beautiful literature examples of beautiful work, for instance, for single molecule conductance or electron transfer rates or redox shift. So it's not an unusual choice. They form a strong modular dipole, and they are known for this property. We prepared this linker unit, and it was helical. The dipole was about 18.6 dBi calculated. And I want to emphasize that we prepared 2 different linkers, one a carboxylic acid, which is how the peptide ends, and one with an isophthalic anchor unit. And this will be important later. The molecular design of a peptide also allows to reverse the dipole quite easily in a way, because you have the peptide protected at the 2 ends, and if you deprotect the amino end and you bind the chromophore there, or you can deprotect the carbonyl end and then put the chromophore there. And the anchor group will go on the opposite side. So by using the same peptide linker, you can have a dipole reversal, because the dipole will be up or down or up with respect to the surface in this way. So you switch around the position basically of the chromophore and the anchor group on the same linker. So this is a possibility with this molecular design. This is where we had a bad surprise. We made the first compound with the dipole down. We anticipated that to measure a very large energy shift, but actually didn't bind at all. And this measurement, it's an XPS, which was used to analyze this, the monolayer at this interface, determined that the carbon-nitrogen ratio was way off. So this, and also we could tell that the compounds were not binding properties properly. And we think it's because the carboxylic acid may have formed a hydrogen bonding interaction, was coiled and was not bind very well. So where I left is the fact that the this chromophore double linker anchor molecule that we synthesized was not binding well. And we determined that actually the isophthalic anchor instead was very effective at binding. So we had these two molecules, the one with the porphyrin bridge unit and isophthalic anchor, and then the linker peptide with the dipole and the isophthalic anchor. At this point, instead of synthesizing a new molecule like this with the isophthalic unit, we decided actually to test a different approach. The approach that I've shown earlier, it's covalent, so every molecule has a dipole linker, but we thought about making a mixed layer where molecules without the dipole can be forming a mixed monolayer with a dipole linker only. And this chromophore will feel still a dipole interfacial dipole effect. So this is what was prepared. This is a cartoon. I want to emphasize that just illustrating that we made a mixed monolayer. This was prepared in the Bartinsky lab in the physics department, just by dipping into alternating in solutions of the linker only and then chromophore only compound and forming a mixed monolayer. The HOMO was shift was what was expected, was 0.3 electron volt. That's only half of what one would calculate from such a large dipole, but one has to remember that in this case, it was diluted. Only half of these monolayer is made of the dipole linker, and the other half contains the chromophore. So this is actually the large shift, and that was in the direction and magnitude that was anticipated. So to summarize a little bit this part, what we observed that it's possible actually to design molecules that have a strong and oriented dipole, that this dipole can be used to shift the energy level of a chromophore, a semiconductor, using this approach, and that it's important to design every component of these molecules. For instance, the anchor groups were absolutely crucial to obtain an effective binding. I will finish with this last experiment that was done more recently. So this was one of the approaches in which you can engineer this interface with molecules. In this case, it's a covalent approach. Every molecule has a chromophore, a dipole linker, and an anchor unit. You feel the maximum dipole effect, but the synthesis is complex. You have this other approach, which is more versatile, because you, in theory, could embed different types of chromophores with the same linker unit, but these are diluted so that you have a smaller shift. And the last approach was studied in the Bartinsky lab, actually, with these compounds, was to study an overlayer. So in this case, you form a monolayer just of the linker dipole, and then the chromophore is vapor deposited on top. So you do not have a covalent system, fully covalent system. It's a layer by layer system, if you will, but it could be actually as effective, because in this case, every chromophore feels a dipole. This cartoon shows how this was realized on a single crystal titanium dioxide. And this was done again in the physics department. And you can read this experiment here. And it's the shift in this case was 600 millielectron volts. So a very large shift in the direction and the magnitude as predicted. And this is a supramolecular, if you will. It's a layer by layer approach to form these interfaces using molecules that contain a stronger dipole. So this is to conclude, I wanted to summarize a little bit with some comments. So what we can conclude is that synthetic design, it's very important to engineer or to tune interfaces between molecule and inorganic semiconductors. And one can obtain molecular level control of this interface with some caveats. That it's important to design not only the unit of interest, the photoactive or the redox active unit, but every aspect of this design. For instance, the linker, the anchor group are important. It is a very interdisciplinary field. The experiments that I've shown you involve collaborations between synthetic chemists, physical chemists, and physicists, surface science to probe many aspects of this interface. And I want to emphasize that these are not just relevant for devices, for applications, but really are useful, these approaches useful to study charge transfer from a fundamental point of view, to ask and answer important scientific questions at this interface. One final comment. Beware cartoons. So obviously I have shown a lot of simplified cartoon-like pictures, but by experience, these are very complex interfaces, they're very heterogeneous, and they have to be studied through a multitude of approaches and rigorously to avoid a superficial, I would say, approach to this. I will end by thanking the collaborators over the years, and this is my current group of graduate and undergraduate students. And we work a lot with fluorescent molecules, and every Friday group meeting, there will be fluorescent slides for Fluorescence Friday. And today it's a Friday, so this is a Fluorescent Friday slide for this opportunity. And I thank you again. I apologize for the technical glitch, and I will be very happy to answer your questions.